there's so much about the brain and mind that we don't know. And I think, like, what is the brain? What is the mind is the most basic philosophy question. And until we answer that, at the end of the day, like, the AI is being programmed by humans. So if humans don't know the answer to that, humans can't program that, and we won't get AI that's going to do that.
This is Nathan LeClaire, independent coder and author, and you're listening to Coffee Moguls, the podcast interviewing internet entrepreneurs and icons who are tackling unconventional problems and getting unconventional results. On Coffee Moguls, we do deep dives so you can unpack what's behind their success, so you can get the edge you need in your career and in your business. Most of our guests and audience members love caffeine, so brew up a cup and settle in. Let's drink some coffee. Let's pump some iron. Let's start a company. It's Coffee Moguls. It's Coffee Moguls. But first, the disclaimer. This podcast is for entertainment purposes only and is not financial advice. The opinions are personal and not professional advice. Consult with a financial advisor before making any financial decisions. Welcome, everyone. Today is Thursday, July the 15th, 2021, and I'm very excited to welcome to the show today Anamita Guha. How's it going?
Good. How are you?
I'm doing well, Anamita. Why don't you tell us a little bit about what you've been working on lately?
Amazing. My name is Anamita Guha, and I have a background in a lot of emerging tech. So for me, I've worked in kind of the new field as the new field is coming out to be the next thing. I worked in mobile when mobile was supposed to be the next big thing. I worked in data when right before big data became the buzzword. I've worked in AI, I've worked in quantum computing, and now I'm actually in the process of transitioning back to a role in AI that I'm super excited about. I think for me, a lot of what I do and my interest in emerging tech just comes from who I am as a person. I was born in India, and I moved around a lot when I was little. My first 5 birthdays were actually in 5 different places. And because of that, I just got a lot of exposure to different people, different walks of life, and different problems society has. And as I got older, both my parents worked in tech. I had the newest gadgets at my house all the time. I was very lucky to kind of have that in my house. And I grew up as kind of like a kid on the internet. So I was talking to more and more people around the world, building websites at age 9. And I went on to study cognitive science because I wanted to know why people do what they do and how decisions are made and how we can use technology to kind of bridge communities. I ended up founding my first company when I was in university. And after selling that, I did a blanket search for cognitive science, which was my major, and I got a job as a product manager. So from there, I kind of jumped from different environments, worked in a lot of different startups, a couple of successful ones, a couple of failed ones, and spent some time at mid-sized companies. And I most recently just closed up a around 5-year stint at IBM, where I had initially joined to run the Watson West headquarters in San Francisco to work on bringing new developers into the Watson ecosystem. And then most recently, I worked on building community for quantum computing around the world.
Yeah, that's awesome. So you just love being on the cutting edge, huh?
I do.
I love that. I love the entrepreneurial vibe. So lots to unpack there, but maybe let's just talk first about quantum computing. So that's probably top of mind since you've been working on that recently. And I don't really know that much about it. Maybe you could just give me a quick little 101 on what's going on there, what's the latest in the field, where is it at, and that kind of thing.
Sure. So when you think of quantum computing, I think one of the first things for anyone, the listeners, for you, for everyone to kind of wrap their heads around is quantum computing is a fundamentally new type of computing. So the computer you're using now, your laptop, your phone, any device really, is a classical computer. And the hardware that's in it is different from the hardware that's in a quantum computer. And it's that hardware that truly enables new types of computation and new types of algorithms and discovery that can happen. So on a quantum computer, they take advantage of quantum mechanical properties, which is actually why it's called a quantum computer, and it enables you to do such things. So there's three main differences and three main basics, 101, as you said, that anyone who's in quantum computing should know. So if you're able to talk intelligently about quantum, you should know these three things. And these are just the three principles that make a quantum computer different. The first one is the concept of a qubit. So if you think about a classical computer, it runs on zeros and ones. And that's how everything's encoded. On a quantum computer, everything runs on zeros and ones, everything in between. So this allows you to think about the potential of what can happen because it's exponential. When you think of a classical computer, maybe you're encoding the letter T, it's like 0, 1, 0, 1. You have a combination of like 2 to the 4. But when it's on a quantum computer, say it's a 50 qubit device, then it would be 2 to the 50 times 2 to the 50 times 2 to the 50 times 2 to the 50. So the potential for computation exponentially increases. So that's the first principle of quantum computing, which is superposition. It allows you to be at 0 and 1 and everything in between. The second principle of quantum computing is entanglement. So this allows two qubits to be entangled together. So a lot of ways that people draw a parallel to this is like if you think of a coin flip. I know a lot of PhD physicists don't like this analogy, but if one qubit is ahead, the other qubit that's entangled with it will also be ahead. If one's a tail, the other will also be a tail. There will never be an instance where one's ahead and one's a tail if they're entangled. So now if we're going back to thinking about zeros and ones, if one is a 1, then the other will also be a 1. So this allows and contributes to that exponential increase. So that's entanglement. The third principle is interference, and this has to do with microwave waves. If you think about introductory physics, if you think about ocean waves, if you're into music and DJing and think about how you like combine sounds, or even noise canceling headphones, right? So how do waves interact with each other? So a quantum computer, the way you access it now is through your classical device. So companies like IBM have put their quantum computer on the cloud, so you're able to go and build out circuits, and you can test out different algorithms and different circuits really to see what sort of output you get. The way that works is you configure it on your classical computer, it gets sent to a quantum device through a series of microwave pulses, and at that point it processes and then it spits out something also in the same wave format. So this, if we put the whole thing together, you're on your device, you configure some sort of circuit, and that will then send a wave out to the class. The quantum computer will absorb it. It'll go into the qubit where it's actually being calculated. The qubit is potentially entangled with another qubit. It will then process that, spit out another wave, and that will then go back. It'll be read, and then it'll be given out to you on a classical device, your readout. So what quantum computers are really good at is processing large amounts of information with one simple input and one simple out. So when you get that output, you get a 0 and 1, and you know the readout of what you're doing.
Got it. So it's kind of taking advantage of these physics principles to do really efficient computation. One thing I guess I don't really understand is like quantum physics, it's very generally non-deterministic, right? Like, isn't that kind of part of the struggle of this is depending on how you observe things, the state that they're in could change, and you kind of have to reconcile that after the fact. So is it just that you can do so many of these quantum computations and just take the best batch and that's your deterministic output? Like, how does that work?
They're noisy. So you never get like a very clear 100% answer. Like there's an error that gets associated with it. And you can correct for that error through a series of different things, like figuring out which qubits are maybe entangled with each other, the pulse that you send out. And that's actually an entire field of quantum computing, quantum error correction, where they are testing that out. In terms of just nature and humans and everything, like nature is inherently quantum mechanical. It's a really famous quote from Richard Feynman, who a lot of people attribute as the father of quantum computing. And when you think about what's happening in the world, and if we're trying to simulate that, a quantum computer is the closest that we'll get. And it's not going to be perfect because we're not perfect. And in order for us to be that deterministic, maybe we don't want to be, because that's not what the world is. and having that little room for error is maybe okay. And that number's changing. I think that's constantly being researched, and people are figuring out how to make it more of a definitive 0 and 1 versus a 0 and 1 that's a little fuzzy. And anytime we add a new qubit to a device or we change up the configuration, it's going to change up this fuzziness.
Does that just impact the performance? Like, you can get deterministic results. You would have to, I would think, right, in order for it to be useful for computing. But then is it just that the more errors that you have, the more inefficient it is? Like, you have to retry it or something like that?
Yeah, I wouldn't say necessarily inefficient. I would say it is inconclusive, maybe. And I think that's okay. I think quantum computing, from my perspective, I think it's pretty far away from being useful. And we're still putting together the hardware and then building the software layer on top of it to create these applications and useful algorithms for us to really create use cases that are very beneficial in a quantum computer. I think the promise is there. I think we just have to keep working towards it and making these discoveries to get ourselves there. I personally also don't envision a world where quantum computers will replace classical computers. I think they will coexist and they will serve different functions based on different needs. Like, you will never use a quantum computer to like something on Facebook, but maybe you will use a quantum computer to find a bone marrow match. But that sifts through a lot of different dimensions of data to get you that, is this a match or not? That's not a use case that's commonly talked about in quantum computing, even now. But for me, as someone who's kind of like futuristic and very optimistic, I could see a world where technology is being used for good, for things like that.
Yeah, exactly. I was wanting to ask you about that. First of all, what does the percolation outward look like? Who gets it first? And then what does it look like as it percolates outwards to Main Street?
Yeah, I think that's honestly, it's a really difficult and important ethical question that everyone should be asking. As someone that's always worked on kind of the cutting edge of emerging technology, it's something I'm constantly asking myself in any environment I'm in. And I firmly believe that the way we talk and use technology now will influence how we use it in the future. I always use an example of visual recognition. The city of San Francisco, for example, has banned all visual recognition, computer vision by the police, whereas the city of New York actually uses it and has been using it for a long time. So the legal policies and the things that get made will be affected by it. The data that you input, the data that you get to build out these sort of algorithms is going to be important. The access you give to different people for quantum computers is going to be different. So there's many ways to think through this and determine what is the next step of who gets access to quantum computers. So I think this is something that IBM did very well. We were very focused on making it open access. I think by putting the quantum computer on the cloud was one of the biggest first steps we could have taken. In order to use a quantum device, you needed to have physical access to a lab and use it. So it was only accessible to PhDs and people in academia for them to use it. Or if you were in industry, you'd need to build yourself your own quantum computer. Now with the quantum computer on the cloud, anyone from anywhere with an internet connection could access it. So I think we've already democratized it in a way. That being said, I think there is a gap that we need to fill in terms of skills development and really setting the right boundaries in what quantum computing can do. I think for artificial intelligence, a lot of people have this innate fear that's going to take over my job and I'm going to become rendered obsolete. I think it's very important for others to just get educated and gain their own perspective on it. So how do we get the next generation of the workforce quantum ready to actually do useful things on a quantum computer? And this goes beyond the developer. It goes to the social media manager that's posting about it on Twitter and informing the public. It includes the product managers and the tech execs that are deciding where to spend money to build different use cases and uses for it. But all of that starts with access to hardware. And if you don't have that access to hardware, you're not going to be able to do constructive things.
Yeah, I didn't even know it was available like in the cloud. There's someone that's just sells it where you can just kind of go sign up and do like Elastic Quantum.
Yeah, they're not selling the quantum computer, but they're selling access to it. So you can run jobs effectively on a quantum computer. So if you think about like an AWS queue, it's a queue to different quantum devices. You can pick which device you want to use that's has its own set of qubits and like configuration that you can test out. Consider it its own like address, and you could just put yourself in the queue to use it.
Got it. Sounds almost like the old days where you share access to this like one singular piece of hardware and it's multi-tenant. So a couple things I'm curious about there. So is that practical today? Like are people doing things and then getting results, for their business, or is it still very research oriented?
From my perspective, I think it's very research oriented. I think a lot of like quantum computers are different from supercomputers, and I think for supercomputers, they're already at a state where they're able to do functional things that a quantum computer can't do yet. But there are things that a quantum computer is promised to do that we haven't ever done before. For example, if you think about just like chemistry is one of the spaces where quantum computing is poised to make a big impact. We've never actually been able to, like, do you drink coffee or tea, right?
Oh, I love coffee. That's why it's the Coffee Moguls.
Oh, there we go. And others listening also drink coffee. So I want you to imagine like a caffeine molecule. It's kind of a complicated molecule. We've never till this day been able to simulate this caffeine molecule because there's so many interactions that can happen. With a classical device, we've been as close as maybe like hydrogen or maybe hydrogen beryllium, but to really get past that basic molecular state, we need a quantum computer to simulate that. So that's something that a quantum computer, as we kind of add more qubits, is going to be successful in doing. I think caffeine is one of those basic molecules, but when you start thinking about more complex molecular structures that are required for drug discovery or other things to test out interactions with the different drugs, a quantum computer is going to be very successful there, as long as we continue to build the right way. So those sort of things, I think, is where quantum computing is going to be very good.
Yeah, that's kind of what I was wondering about, like protein folding and that kind of thing, where we're maybe bottlenecked by compute, if it could kind of help out there.
Yeah, and like you asked about research or industry focus, right? I think the industry focus applications are there. We're just, from the research standpoint, not there yet. The quantum computer is only as useful as the hardware, and what you're kind of seeing is different companies, different research labs, different institutions around the world are experimenting with different methodologies of how to build a qubit or how to send different pulses. If we go back to that basic picture we had drawn, there's different methods to do everything, and everyone's testing it out to see what's going to work. And once we get past this point of this is what's working and this is how well it's working, if you go to your deterministic question, right, then we can put all that together to say, like, here's an application that's useful, that's going to better society. But right now we're still in the research phase.
Yeah. Doesn't this kind of break all encryption? So are we hosed? Like, what happens when we can just suddenly do really efficient computation on this stuff?
I think, like, when I even started working in quantum, that was the first question I had, right? And how far are we from that? I think then, like, the short answer is it can, but the real answer is we're not there yet, and it won't for a while. So will there be a point where everyone needs to kind of redo their encryption? Yes, but that should happen anyway, and it naturally has been happening. If you look at the history of how things are being encoded and encrypted over time, there's going to be hackers, there's going to be new technology, there's going to be new storage, everything's going to change over time because technology evolves. So this is a part of that natural evolution of how technology is. So I wouldn't take this as like oh no, we're going to go into this future where like people are hacking into our, I don't know, electrical grids and we, like, those actually are not even encrypted to begin with. But I think when we do think about long-winded passwords and long-winded things that are encrypted, I think we're still far away. And there's a lot of people that are motivated to do research in that field and are doing research in that field. It'll be costly. It'll be costly to kind of update it, but it always is.
Right. So maybe it'll end up being one of these Y2K kind of deals where theoretically it could be a problem, but maybe everyone's so aware of that and everyone's so ready and prepared for it that by the time the threat actually materializes, it's not as big of a deal as we worried about.
Right.
Is there anything disruptive or worrisome about it that people are not thinking about?
I think people are thinking about it. For me, it's down to access. Like, who's using it? Who are we giving the forefront to? How are we making sure that, like, global perspectives are taken into consideration? Something I did a lot of when I worked at IBM and quantum was building the global community. So For me, I had individuals on my team reporting to me from around the world who were actually spread across 11 time zones. So even holding a team meeting was very, very difficult. But what this enabled us to do was really have a solid pulse on the world and how problems and how the education system is different. So the example I always think of is set theory. So I didn't learn about set theory until I took college level discrete mathematics. But in India, for example, you learn about set theory in kindergarten. So the way that you kind of get started with your mathematics education or even physics education or computer science education will definitely change how you are thinking about getting started in a new field. Now, the other layer to that is the applications and the problems. So everyone has unique problems that they're trying to solve for in the world. So when I was in South Africa and looking through different tech accelerators there, the types of problems that they're thinking about are very different from the problems that we're thinking about here in San Francisco or New York or other parts of the more developed world. For example, in South Africa, one of the applications I think about often is how they do pill delivery for prescriptions. So similar to how we have Amazon lockers here, they created an Amazon locker-esque thing that enabled individuals to walk to this locker and pick up their drug prescription that they need to survive. So those are the sort of problems that they're thinking about because they don't have a local CVS nearby to grab what they need. And I think being aware of those sort of problems and the educational foundation that people have is very important. And I don't think people are thinking about that enough. So you take that as the very basic problems and the foundation. Second layer is all the things that are kind of intangible. So what are the different, maybe injustices is the right word, that exist, hidden layer of society that influence different things. So are there certain biases that we need to be aware of? Are there certain historical significances that we need to be aware of? So really making ourselves aware and culturally competent about what's happening in different parts of the world is very important. So you have the more tactical foundation and the problems, but then what's the curtain on top of it that we also need to think about and pull back. And then the final thing is, who should we maybe not give access to, and who should we maybe include in the room when decisions are made. So in any ethical conversation, I really think it's important to have a philosopher in the room. And that's my personal opinion, but having someone that really challenges ourselves and our questions to think about, okay, how can we look at this from different angles? Should we have economists in the room that thinks about how this is going to influence global trade and think about how it's going to influence overall structure? Should we have legal policymakers in the room to think about what sort of legal policy is going to come up or how long it will take for us to actually pass something? And then the most basic thing is do we want to somehow, I don't know if regulate is the right word, but have a perspective on what sort of use cases can be tested? Should we give access to government so that they can use this to develop nuclear power? And those sort of things is a debated question. And once you kind of have the perspective of here's the education system, here's the applications and questions that we want to solve, combined with the overall unwritten truths, how do we kind of handle and regulate and think about those questions with the right people in the room?
Right. Yeah. My degree is in philosophy, so I volunteer to be the philosopher in the room anytime. Anytime. We can hash out all sides of the debate. So what do you think will be the best areas of application? You kind of touched a little bit on bone marrow matches and protein folding and that kind of thing.
So for me, I think there's so many spaces. I think chemistry, biology, that sort of simulating the natural world, I think is very, very big. And I think if we do it right, we'll get ourselves there. I think another space is logistics and finance. So anything there's a lot of data that we need to kind of sift through to make sense of. I think quantum computing is going to do a really good job at. And then this might be motivated by just my personal interest, but I think in quantum machine learning, there's a lot of potential. And machine learning as a field in itself is still being evolved. And I think any algorithm you create on a classical computer can't actually be directly ported to a quantum computer. So the search algorithm, or even just y equal mx plus b, the way that's written on a classical computer is written differently on a quantum computer. So we're starting from scratch. But the benefit is we know where we want to go or different things that are possible. So you can test things out simultaneously and really advance the field of machine learning. And I think if we think about the different layers of machine learning and the different applications, if we can kind of find this sweet spot where we can coexist and really use data to help us solve problems that we've been thinking about, it will allow us to think about even larger problems. Like if I've mentioned many times that people have this fear that AI is going to take over their jobs. I'm of the belief that AI is not artificial intelligence, but it's augmented intelligence. It is there to make you efficient, to use your word, Nathan. It is there to help make faster decisions, stronger decisions. There will always be a human in the loop, but it's there to help you augment what you're doing. Now, if you have these simple tasks that you're waiting for maybe a classical computer to solve for a long time and it's done quicker, you now have more time to think through different scenarios, maybe even think about problems that we haven't even started solving, like what are we going to do about climate change,
Yeah. I mean, that makes perfect sense. I think one of the reasons deep learning became popular was just because it fit GPUs really well. And so I got to imagine in quantum, similar things will happen where the algorithms and the kind of techniques will evolve to fit the hardware, basically. I'm not too worried about AI taking my job. Worst case, I'll just go full beard. I'll become a philosopher, and I don't think AI will be taking that job.
You'll be okay. I even think if you think about the human brain and mind, I'm a cognitive scientist, right? There's so much about the brain and mind that we don't know. And I think what is the brain? What is the mind is the most basic philosophy question. And until we answer that, at the end of the day, the AI is being programmed by humans. So if humans don't know the answer to that, humans can't program that, and we won't get AI that's going to do that.
Right. We're really a long ways away from general intelligence, and whether it's supervised learning or whatever, it's only as smart as what you pointed at.
Right. It's only as smart as the person behind it that's programming and the data that it has. So if we go back to that example I was sharing about what we should be aware of, we also need to work on removing the biases that we have, and then making sure that that data is not biased. And it starts from the data we decide to collect, and the data that we decide to label, and the data that we decide to refresh, and then how we design the algorithm and how we learn from it and the questions we ask. So that's why it's important to have people from diverse perspectives, diverse walks of life, diverse global perspectives to really be in the room to challenge each other and be okay with that.
Totally. We've seen some really embarrassing things come out of the field. And we still don't have a Zoom background that works well with Black people's skin, right?
Yeah, I mean, that's one of many, many examples. And I think for AI, about 80% of code is actually not released. So if you look at archive papers, people don't open source their code. So everyone has to kind of start from scratch. And I think that's one of the first things you can do is make your data sets public, make your algorithms and what you're testing out open source. Let's all build with each other. And I know that's, again, a very positive view that's never going to exist, but maybe it can. And if maybe one or two people that's listening today can say okay, I'm going to open source something I'm doing, or I'm going to ask for someone's perspective that I haven't considered, I think that's a win.
Yeah. I mean, it starts here, right? With conversations like this and kind of spreading that meme around, and reproducibility. That's a really interesting problem. So that's actually a really good segue. So your other interest is really strongly in AI and in machine learning. What's got you fired up?
I think a lot of it is, there's a lot. where should I start? I think the main ones is how do we get more people in the room working and building AI? So for me, I'm really, really passionate about getting more women and girls into the field of emerging technology, artificial intelligence, and how can we get there? So in addition to my work, I do a lot of work as a ambassador for the American Association for the Advancement of Science. And in that capacity, I do a lot of public-facing work to say, here is what a scientist looks like, or here's what you could do to really inspire the next generation of female scientists and entrepreneurs. So just making sure that we have the right people in the room. I think the other space that I'm very excited about is privacy. So what does data privacy look like? How can we make people empowered to make decisions on their data? Because at the end of the day, anything we build with AI is powered by data. So if you think of the AI to be a rocket ship, the fuel that you put into it is the data. So without the fuel, it's not going to go anywhere. and what are different things that we need to consider to really balance this like delicate dance of making people aware of the data and how it's being used, but then needing that data to advance the algorithms and make real change.
Totally. Yeah. So the data, I mean, do you think there's a lot of potential out there for even just new technologies that help people kind of shape the data, pre-prepare it and pre-process it and that kind of thing? Like what's going on in the field there?
Yeah, there are. There's even AI that's labeling the data for you. So there's humans that are doing it in like data mills in different parts of the world. There's people that are doing it themselves that they can send it out. There's AI that's data labeling for you. But again, this goes back to the bias. So how you label data is determined by who's doing it and how it's being programmed to do. So I think having those checks and balances in the data layer is probably one of the most, and people are thinking about it. And how do you, like, people are even building like bias removal kits and other things to it. There's a lot going on there. It's definitely a hot spot.
Yeah, that's interesting. The right labeling and picking the right features and avoiding overfitting is a huge concern there. So we got to wrap up. Is there anything you want to cover that we haven't covered yet?
I don't think so. The only thing that comes to mind, I don't know how many of your listeners are parents or high school age girls between the age of 13 and 18, but I have launched an initiative called Girls of the Future. So if you go to www.girlsofthefuture.org, we're looking to identify high school age girls that are working in emerging tech. And our thesis is the best way to get more women in STEM is to showcase their peers, their best friends, their neighbors. So if you know anyone that fits into this build, I would encourage you to go to www.girlsofthefuture.org and nominate yourself or someone else.
Right on. Well, I'll make sure to link that in the YouTube description.
Amazing.
Yeah. So thanks very much for coming on. I had a great time and I'm really excited for you.
Thank you, Nathan. Thanks for having me. And thanks everyone for listening. I'm pretty active on social media, other places, so feel free to follow along my journey there. And if anyone has any questions about quantum computing or anything, feel free to reach out and I'm happy to answer however I can.
Great. I'll make sure to link your Twitter in the comments too.
Great. Thanks, Nathan.
No worries.